good evening, everyone. While we're waiting for some of our additional attendees to join, I'm going to go ahead and get things kicked off. My name is Pete Eberle. I'm with NCRES. We're the northern chapter of the Colorado Renewable Energy Society. For those who are not familiar with CRES, we're a 501c3 not-for-profit celebrating our 25th year of being educator and advocator of renewable energy here in Colorado. If you're interested in learning more about CRES, I suggest that you visit our website at cres-energy.org. That's CRES-energy.org. There you can learn more about our history, sign up for newsletters, follow links to our social media feeds through Facebook, LinkedIn, and Twitter. We also have links to our YouTube page that has over 140 video recordings of previous presentations, such as tonight's. You can also look at our event calendar and find out the upcoming events across all of the chapters of CRES, including NCRES in the north. We've got a Boulder chapter, which is BCRES. Southeastern Colorado, that's based out of Colorado Springs, that's CCRES. Metro Denver CRES, and Jefferson County CRES. You can also help support us by donating or becoming a member. Speaking of members, I do want to give thanks to our Northern Colorado business sponsors, which include Solaris Energy, Platte River Power Authority, Poudre Valley Rural Electric Association, and Sandbox Solar. Before we get started, I do have a couple of event announcements. Coming up here on May 4th and 5th and the 14th is the 21st Century Energy Transition Symposium. That's being hosted by the Colorado Energy Research Collaboratory. I will try to send out a link to register for that, but if you you can basically Google that and find it pretty easily. It's all-day events on the 4th and 5th, and almost 3/4 of a day on the 14th. Really great event. It's the 9th annual version of that, and CRES is one of the supporting organizations. In terms of CRES events, on Monday, May 10th, 6:30 to 8 p.m., the CCRES chapter is hosting Dwayne Hiley, the CEO of Tri-State Generation and Transmission, to discuss the Tri-State Responsible Energy Plan. And then Thursday, May 20th, the Metro Denver chapter is hosting a Roadmap to 1 million EVs by 2030. A Colorado consumer journey and barriers, and that will feature Bill LeBlanc of eSource, which is a sustainable energy consulting firm out of Boulder. That'll be at 7 p.m. on Thursday, May 20th. And again, for those events, if you're interested, just go to cres-energy.org events, and you'll be able to either log into the meetups, or if you just want to register to the GoToWebinar links. So without further ado, I'm going to go ahead and hand it off to Leland Keller of Fort Collins Utilities, Matt Scherer of REenergizeCO, and Ian Skor of Sandbox Solar.
Thank you, Pete. And good evening, everybody. My name's Leland, and I manage the battery storage program, the residential solar rebate program, and the community solar program for Fort Collins Utilities. And I'm really excited to be with you this evening for this conversation about battery storage. I think that this will be a really important part of the solution set as we work to achieve the goals of delivering increasing shares of non-carbon energy in Northern Colorado. You know, about 2 months ago, Winter Storm Uri caused extended power outages across Texas and many other places as we were planning this very event tonight. That winter storm and the rolling blackouts across California in 2020 and even 2019 that were spurred by wildfires and wind events got a lot of people thinking about what batteries can do for them. Closer to home, Fort Collins Utilities' implementation of the time of day rate structure back in 2018 spurred a lot of installations coming online in Fort Collins. So we've seen a substantial growth in the interest in batteries locally since the very first one in Fort Collins in 2017, up to 65 systems now installed or in development on the Fort Collins utilities grid. So I've shared with this group before about the launch of the Fort Collins Battery Installation Incentive back in June 2020. And that's still available. We can talk some more about that later if you're interested. But tonight, we're really going to be focused on some of the details that you'd need to consider when selecting a battery storage system. And I'm really excited to share the stage with two of the leaders in the Northern Colorado solar and battery storage market. Both have built respected businesses that are based in Fort Collins. And I'd like for you guys to introduce yourselves. Ian, how about you start first?
Yeah, thank you, Leland. I'm Ian Skor, the co-founder of Sandbox Solar. We're based out of the CSU powerhouse. We've been installing residential solar for the last 6 years. In the last 4 years, we've been installing battery systems of all kinds, all the way from off-grid mountain cabins to on-grid solar and battery solutions to microgrids. So excited to share tonight.
Hey, Leland, thank you. My name's Matt Scherer. I'm one of the owners of REenergize here in Fort Collins, and we're about 30 employees from Fort Collins to Denver. I run everything on the solar side of the business, also oversee a portion of our northern efficiency business as well. And thank you guys for joining tonight. We're excited to be here.
Thanks, Matt. Thanks, Ian. So tonight we're focusing on grid-tied battery systems. And so just to ground this conversation in some common understandings, we're going to assume that we're talking just about considerations for a battery system that is installed for residential use. And we're going to be talking about grid-tied solar plus battery systems only. So tonight we're not talking about the cabin in the woods up by Red Feather Lakes, where that's completely off the grid. We're talking about systems that are installed in houses that are in some way or another tied to the electric grid. Just a point on some terminology that will probably come up later in the conversation this evening. We may be talking about AC coupled versus DC coupled battery systems. An AC coupled battery system is electrically connected directly to your main distribution panel in your house, and an example of an AC battery system would be a Tesla Powerwall or a Sonnen Eco unit. What you see in the image on the screen is a DC connected battery. That's a DC battery that's connected to the same inverter that is supporting the solar PV system on the roof. So that's a distinction between AC coupled and DC coupled batteries. The string inverter versus micro inverter is something that many of you are probably familiar with. String inverters are really one inverter, as shown in the image on screen, that's serving all the solar modules on the roof, whereas micro inverters are really small inverter technology that's installed right on the back of the solar module up on the roof. Moving along, the main point we want to drive home tonight is that while you may have in the back of your mind the idea that a battery might be really good for me and my solar system, I think one day I might get a battery. But what we're talking about tonight is batteries have obviously a lot of different shapes and sizes. You're familiar with the kinds of batteries that are shown here on the screen. And if somebody called out to you and said, hey, I need a battery, go get me a battery, you would need to know, well, what kind of battery are we talking about? What is the specific function of that battery? And what's it designed to do, right? Am I going to the store to get a 9-volt battery, or AA batteries, or a hearing aid battery, or one of these disc batteries to open the garage door? What kind of battery are we talking about, and what is the function of that battery? So we'll be making some similar distinctions in the different kinds of use cases for residential battery storage tonight. But I wanted to bring that back to the kinds of batteries that you may already be familiar with. So moving along with that, there are some essential questions that you're going to start with when you're beginning to select and size a battery system. And the first one of those is really understanding what kind of problem are you trying to solve, or what do you want to achieve with that battery installation at your home. And then, there are some cost implications of making this choice too. $10,000 is a good round number for a starting point for that conversation. And then how big do you want to go? How much do you want to be able to accomplish with that battery in terms of running loads in your house? So those are some of the simple questions to start with. And tonight we're also going to talk about some of the other considerations that come into play when designing a system to serve your home. I'm not going to go through all of these bullet points now, but we'll just touch on several of these as we go through some specific examples later in the presentation. There are primary and secondary use cases for your battery system. In many cases, people may be interested in having some resiliency in case the grid goes down, for example. If that's the primary use case, then you'd really be designing that battery system to take care of your house in the event of a grid outage. Or perhaps you live in Fort Collins, or and you're interested to save the energy that you generate in your solar system during the day, so that you can avoid paying the higher price for on-peak energy. And so you might be interested in doing what's known as a time of day arbitrage, essentially storing energy that you can use during those high on-peak periods, high price on-peak periods, to reduce your bill, or even sell energy back to the grid and earn credits. We'll also be talking about some of the boundary conditions, like net metering rules and rates, as well as your personal goals, and like how much of the loads in your house do you really need to run on a battery system if the grid goes down. And finally, there are other design requirements to be considered when designing a battery system that might be specific to your house, such as where the batteries would be located, and other sizing requirements that might be unique to your electrical system. When you got the email from NCRES about this presentation tonight, we promised to teach you about the simple approach for sizing batteries. So I don't want to create too much confusion with all the considerations on that last slide, but the simple approach is really to consider when sizing your battery to consider how much load you have to serve, and that's typically measured in kilowatts, and how long of a duration do you want to serve that load in your house. Simply speaking, if you have a 1 kilowatt hair dryer and you want to run that 1 kilowatt hair dryer for 12 hours, you would need a 12 kilowatt hour capacity battery system. I hope that makes sense. That's just a very simple example. But as we approach that battery system design, you would add up the loads in your house that you would need to serve in the case of a grid outage if we're sizing for resiliency. And so you'd think there of perhaps your refrigerator, some lighting, chargers for cell phones, and perhaps your Wi-Fi router, things like that, that you would really want to be operating during a grid outage. And then you would plan for the duration of that outage. Do you think that you need to size that battery system for a 3-hour outage, or to size that to be able to endure a 24-hour outage, anticipating that the sun's going to rise again and you'll likely have some generation to replenish your battery. Obviously, this winter storm in Texas illustrated that the grid can go down when there's snow on your panels. So that's something to consider about how your solar system may be impaired from recharging your battery if the weather's bad. Anyway, in this approach, we're illustrating how you would take your primary use case and develop your design, model the performance of that design, and then continue optimizing that design in consideration of other elements that we showed on the last slide, adjusting for intermittent renewable generation and that duration that you need to support your house without power from the grid and so forth. And continue optimizing that design for your considerations, not the least of which is the financial cost, until you arrive at what would be just right for your situation. Now, as we get into the details of this conversation tonight, we're going to illustrate these through some real-life examples in Northern Colorado. And I actually want to pass the mic over to Matt at REenergize to talk about some of their installations and examples for you.
Leland, thank you. I think that was an awesome start. You know, Leland said something that I think super important, which was the simple approach. I think about batteries, kind of where batteries are today, very similar to where solar was about a decade ago. It's a newer technology, it's changing a lot, and it's really easy to really overcomplicate it. So my approach, and the approach we kind of take as a business, is to really try to make it simple. And to start off, I think there's two flavors or two kind of versions of storage, and this is kind of terminology we like to use. I think there's grid-tied storage, and that's really where the financial benefit is both known and most likely, as well as the environmental benefit, and then there's backup. So I think for the purpose of this conversation, we can all probably agree that we're looking at about a 99% to 1% ratio, generally speaking, in these two areas. And then when we think about design criteria, there's two here as well. There's power and energy. I think with this audience, most of you already know this. in a DC coupled system, power typically for a single unit is somewhere in the area of 5,000 to 7,000 watts, give or take. And that's limited in two ways. It's limited by the device, being the battery, and it's also limited in whatever is actually converting the DC to AC, which is in the inverter. And those are stackable, so you could double that and get additional kind of capacity on the power side. On the energy side, it's really a function of the battery. This is true storage as we think about it. It's how much energy is in a specific device that's usable. And okay, so 7,600 watts. If anybody's looked at kind of data sheets or different inverter specs, you see this kind of this wattage number thrown out a lot that tends to be in the 7,600 range, and that's not by chance. It wasn't some marketing group that thought that would be a good thing. It's actually driven by a lot of electrical code and a lot of practical applications. And where this comes from is 7,600 watts is kind of this number that works out to about a 40 amp interconnection. And this number matters for a host of different reasons: wire size, equipment rating, also service panel rating. So you'll tend to see in the SolarEdge, in the Generac, in a lot of these other inverter manufacturers, they kind of have a design built around this capacity of about 40 amps of interconnection, and that works out to about 7,600 watts. You'll also see a lot of battery manufacturers that match that. If you remember the previous slide, I talked about kind of the two components on the power side. It would be great to have a battery that spit out 10,000 watts. Well, if the inverter running that can only handle 7,600, then you're leaving some energy, you're leaving some power behind. So you tend to see this kind of matching of battery power and inverter power. When we talk about what's practical, I think it's really important for everybody to kind of keep in mind that, again, we're talking about realistically, no matter who your utility provider is in Colorado, we're talking about 99% plus uptime, service level agreement, uptime of the grid. So is it possible to design, a 200 amp off, backup potential that's going to run for a week? For sure. My question to everybody is that practical? And does that actually help us from an environmental perspective? Does that actually help us from supporting the grid? I'm going to use a term that I think we all know all too well, which is flattening the curve. In my opinion, the best application of a battery isn't backup. It's really about taking this big production curve and squashing it down and spreading that power out. When first of all the grid needs it most, which is after the sun goes down, specifically around time of use rates. That's kind of the known benefit more and more financially as utilities adopt time of use rates. But it's also the environmental benefit, because that's the hardest time to put green energy on the grid. So that's a big piece of this. So from a design philosophy, we try to design around the uptime and maximize the value of the battery based on when it's going to be deployed. And again, 99%, give or take, is kind of a good number to think about. I think it's a practical, application for this. And then that also has a very high ROI, I should say a known ROI. Backup is really in the value of, the end user. And there's a lot of variables there. You have to think about, when the grid is actually going to go down, how long is it going to go down, and that kind of comes back to you know, one of, again, personally and professionally, one of my biggest design criteria is we're big on putting the control of that battery in the hands of the end user, specifically the control over kind of what's going to be backed up, how long. Again, there are a lot of variables there. So in my opinion, I think a whole house approach, having the ability as an end user to look at how much power that the house is actually using, make smart decisions around what you're going to try to turn on and when, what the weather's like, are the panels going to make power the next day. When we talk about backup, those are kind of the things that I think matter, and we'll talk about. I'll show you some examples about that here in a second. So we're going to look at two quick examples here. The first one is a huge ranch in Longmont. Ton of horses there. Beautiful property, but there were some backup concerns because they've had outages there. And when you think about, you know, livestock, horses, water, that kind of thing, backup was a very important piece of that. So this is about an 11.5 kW system, solar system. There's two LG Chem batteries, so 19.6 kilowatt hours stored. So this is a DC coupled system. It's a single inverter. So it's a single SolarEdge 7600 model inverter. We'll talk about that in a second as well. And it has, you know, full backup. So there is 200 amp service coming into this property, and we're realistically protecting that entire load panel with a single inverter and only, you know, effectively 19.6 kilowatt hours stored. And the next example we're going to talk about is in Fort Collins in the city. So this is about a little over a 12 kW system, two batteries, again, DC coupled. Now this is, again, coming back to that previous slide, this is grid tied storage. So there is no backup component. If the grid were to go down in the city, this system would shut off, no different than a regular, you know, grid tied system. It just happens to have storage. If you look at the uptime in the city, again, this is really designed around maximizing the value with our time of use rates here in the city. So coming back to that Longmont system, we talked about kind of control. I like to think about batteries as a 10-year consumable device. So if you take that approach and put that hat on, I think it makes sense to use that battery as best as possible in the time period you have. That's generally speaking the warranty for batteries like this. So the idea is to configure them to really benefit as best as possible the condition they're in, which is to benefit the grid, support the grid, again, flatten that curve. So if we look kind of here in this middle picture, this is 12:01 a.m. here right in the beginning. That green is all base loads in the house. The system's basically locked on to how much power the house needs. The battery is feeding that. Sun comes up, makes a ton of power, it charges the batteries here. Sun starts going down, and you can see again here, it's just locked onto the load profile of the house. So in the screenshot where we're at, the house is demanding, you know, 2.6 kW, about 2,600 watts. The system is feeding that exact same amount. It's just all coming from the battery down here. So this is an example of what we call behind the meter energy management or maximizing self-consumption. The other unique thing about this, I mentioned earlier, this was effectively a 7,600 watt inverter. Well, most of these DC coupled systems have a very high DC to AC ratio, sometimes 2 to 1, sometimes a little bit less than that. But if you didn't have a battery, you just had a 12 or larger kW system and only a 7,600 watt inverter, you're going to clip. You're basically going to have a flat top right here, because you can't convert to AC any more than about 7,600 watts. These systems generally don't work that way. They can take up to, again, 2 to 1. They could take potentially up to 15 kW DC in. They might only be able to invert 7,600, but they can take the rest of that energy and shove it into the battery. And that's what you're looking at right here in this screenshot. The system's producing significantly above 7,600 watts. So it's exporting a good portion of that in AC onto the grid, but the rest is charging the battery. So this is an example of a battery really behaving and benefiting the system in a way to, again, flatten the curve, capture energy during that highest peak of production, and instead of clipping or leaving it behind, putting it into the battery for storage to deploy it later, again, when the grid needs it the most and where the most financial and environmental benefit really is. So we'll talk about that Fort Collins, city of Fort Collins example. So Fort Collins Utilities has been on time of use for a little while now. I will tell you that PVREA has a pilot out, Excel has a pilot out. Time of use isn't an if, it's a when. So one of the things we're pretty big on is these flexible, scalable systems. We have all the programming written already for utilities that have time of use to follow a specific profile based on the utility rates that are in place for that location. So when we talk about this system here, we're going to look at just kind of 4 months of use. This system is, if we just look at production, this system's already made, pretty good amount of power, more energy, more than what they've needed. So they're getting a benefit there. But if we look at the export, it's already exported, 2,500 kilowatt hours. Of that 2,500 kilowatt hours just through the programming, a significant portion was exported during peak time of use rates. And that is purely a function of the programming of this system and of the battery profile. And if we want to talk kind of financial numbers, really numbers about this works out in just 4 months to $330 by exporting at that peak time of use rate. Now, if you didn't have that, certainly you would be having export, but it would be, a third less of that value. And that's typically what we're seeing across utility rates, is about a 3 to 1 ratio between, off peak and on peak. And then I'll add about this, that these are generally about the worst 4 months out of the year in terms of solar production. Generally speaking, batteries don't care about that. They're going to behave the way they're programmed to behave. So regardless of what these numbers might have been in terms of, export, did they make more than the roof made? It doesn't matter. The batteries are going to do exactly what they're programmed to do based on the time of use rates. So looking on the right side here, we've got a little bit before time of use. For everybody that's not familiar, time of use rates in Fort Collins in the winter is 5 to 9 p.m. So here we are a minute before 5. The roof's still making a little bit of power. House is consuming a little bit. It's pulling some from the grid. But take a look at these batteries. They're sitting here at 100%. And then literally a minute after 5, yes, the roof's still making a little bit of power, but look what these batteries are doing. They're running to the tune of 5 kW more than the house actually needs. So they're covering all the loads in the house. They're shoving that onto the grid, and they'll continue to do that until they're basically at their minimum state. And that is the end of my slides. Peter, I'll let you kick it over to Ian.
Okay, Ian, you're up.
Excellent. Well done, Matt. I love the approach and can't agree more with all of that. So before diving in, there's a lot of battery companies that are commercializing on the market. I think Matt and I have both been using the SolarEdge LG combination just because it makes a lot of sense for the simple approach. And I'll go through another simple approach example here in a minute. But as you know, there's other battery manufacturer companies such as Enphase Energy for the microinverters, which is unique AC coupled tied system. There's the notorious Tesla systems. There's Sonnen, which are extremely great for micro-islanding and smart grid technology, software technology. And there's a lot of ancient battery companies that are creating more solutions for the various types of applications. And over time, we'll really start to see different kinds of manufacturers coming out with various cell technologies for various types of applications, whether it's for your vehicle to grid, home backup, time of day rates, long-term energy storage. There's so many different applications for batteries. And so that's really the reason for the excitement of batteries and why we're about to see that exponential adoption here soon. So to come back to a simple solution design in Fort Collins, this customer got just a standard 5 kW solar energy system, and they wanted to add a battery to their system and see, if they can maximize the use out of their solar energy within Fort Collins. So as the benefit of the LG Chem battery solution is it connects, it DC couples right into the inverter next to it. So there's really not a ton of components that are required in order to connect these types of batteries to the Fort Collins grid. That reduces a lot of upfront costs. So when you start adding backup power, then you have to add more components. In this case, it's purely for grid play, and it's an pretty much easy plug and play. So it's a 9.8 kilowatt hour battery, and you can program it to all your needs. There's various types of applications available, but we've really programmed a couple solutions for customers within Fort Collins to maximize their interests. On the right here, you'll see the first yellow line. So this customer just wanted to cover their loads during general time of day rates, but they didn't want to completely discharge their whole battery right away during time of day rates. So they simply cover their loads, which is that slow discharge over a few hours during the time of day rates. Then as it comes to the last hour and a half of the time of day rates, they wanted to discharge the rest. And so that's kind of a unique example, simple example of day in, day out. They charge their battery, simply cover loads during time of day rates so they don't have to pay that extra 3 times charge, and then they discharge the rest to get a little extra benefit towards their utility bill. So this is just a base example. There's a lot of different components that go into this. So don't take the cost necessarily up front, but this is a pretty good example of what a break-even will look like on a 2 battery system in Fort Collins. So this would be LG Chem 2. And the key I wanted to point out here is the battery payback. So the battery paybacks are about 10 years, and the batteries are warranted for about 10 years or their cycle period. Now we're starting to see this number go even below that number, and I think within the next few years there'll be a significant financial play. But the key to see here is there's not significant savings yet on the battery lifetime, but we will be seeing it soon. However, if you do have a PV system, I also encourage you to contact your installer and get a quote, because you may have a system where it's easy to DC couple your battery into your system, which might reduce those costs. For example, we had one customer in Fort Collins who gets $40 back every month from Fort Collins because they're unloading energy during time of day rates every single month throughout the year. So this is a unique system as well. This is the new Enphase N-Charge battery system. There may be some people watching that have the Enphase microinverters. Now this year, Enphase launched their new N-Charge battery system with their Empower switch, and I'll go through the components here in a second. This project was undertaken in order to determine how much this customer needs to back up their house with their existing Enphase microinverter system. So the key approach here was to understanding the customer's consumption and usage. So this is the approach I really encourage all customers, even potentially, even if they do, before they do energy efficiency or solar, and especially before batteries, is understanding what you use day in, day out. You may have seen earlier that consumption profile. So you always have an always on period, and then you'll be able to see your AC kick on throughout the day. So from knowing your consumption profile, you can determine from your devices how many kilowatt hours you need to back up. And then your solar installer, your battery installer, can determine where those loads exist and how to electrically set everything up. So you can either back up your whole house or certain loads of your house. So in this example, there's the Enphase Empower switch. Now this is like Enphase's version of an automatic transfer switch, for those of you that are familiar. For those of you that are unfamiliar, the automatic transfer switch recognizes when the utility grid goes down, and it'll isolate the entire home and solar and battery system within itself, so it doesn't backfeed energy to the utility, so your solar panels can continue to work when the grid goes down. So that's how this Empower switch works. And these are the Enphase N-Charge batteries. They come in 3 kilowatt hour kits. So I really like to explain this as kind of the opportunity to start small and then potentially add up over time. That's a great solution, and yeah, it's great to see it deployed. So here's an example of a really robust system. So the Red Feather Lakes Library District was seeking to procure and back up their community in case of a fire event. So they're in Poudre Valley REA territory, and there's only one set of lines that go up to Red Feather. These lines go out oftentimes during severe storms and fire outage events. So that leaves homeowners in the area typically without any sort of power or any sort of backup, especially during a fire outage. So the community came together, pooled their money together, and decided they wanted a really robust system in Red Feather Lake's microgrid, where they could coexist and communicate with the outside world, and first responders could maintain communication and be able to combat fires. So in order to do this, we deployed 6 LG Chem batteries with various SolarEdge inverters, and also deployed a Generac generator. So this is unique because generators now provide the extra resilience with batteries, so you can combine the two within the same controls and same system. So if by chance your batteries did deplete, you'd have a generator on standby, able to generate power either for the batteries or match the profile of the building. So here's the solar installed at the building, and this community is about to go right online with their unique microgrid, which can also feed back energy during peak times to Poudre Valley REA within the community, so that the whole community receives lower peak energy costs. So it's a pretty unique, robust project, and you start seeing a lot of these within our communities and various city centers. And I'll turn it over to Leland.
Well, thanks again, Ian and Matt, for those examples. Obviously, you can see that system that might be designed to serve the ideal needs of one customer on the Fort Collins grid might not work so well for a customer who's, say, out at the end of a long feeder in another service provider's territory and has a different set of priorities. There are some other potential conflicts to consider when you're thinking about how battery design might work well for you. And here I'm intending to just point out how designs that might serve one customer really well wouldn't work so well for another customer's needs, and vice versa. There are some obvious conflicts, like, well, if you want to use your battery system to arbitrage the time of day rates, number one, if you want to charge the battery up fully during the day and discharge it during the evening on peak periods, or to serve your house's load throughout the evening when the sun's not up, you need to start with an empty battery in order to accept that full charge and take the best advantage of the solar power that you're generating. Or so that is to say, if your goal is to store the excess solar power from your roof, you need some space in your battery in order to to accept that. It's kind of like starting with a glass that's full and trying to add more water to it. That wouldn't work, right? So that's one example of just exercising the battery on a daily basis for solar storage or time of day arbitrage. Some other examples here that we're sharing on the screen are number one, for like an AC connected battery that's designed for resiliency with small loads on a backed up power panel. In the design of, say, a Sonnen system or a Tesla system that are AC connected batteries, if you chose to just back up a small panel of backed up loads to maximize your resiliency, again, with just a few loads on that backed up panel, such as your refrigerator and some lights and some plug loads, your battery could last for a long time during an outage. And if you were also wanting to optimize that for arbitraging the time of day rate, you wouldn't have very good results optimizing that time of day arbitrage, because you're only able to use that battery to run your refrigerator and a few loads in the kitchen, for example, during that on-peak period. Your battery is only going to be able to serve the loads that are on that backed up panel, and so you wouldn't exercise much of the capacity in the battery as you're trying to arbitrage that time of day rate, because your refrigerator doesn't use all that much energy in 4 or 5 hours. So while this battery design would be good for serving you over a long duration outage, it wouldn't serve other loads in the house, and it wouldn't be able to discharge energy to the grid, and it also wouldn't generate a kind of a payback that Matt and Ian were illustrating in their examples. Another example in the second bullet for an AC connected whole house battery system, that battery system could be optimized to actually serve all the loads in your house, and you could exercise it regularly for that time of day arbitrage play. But again, the arbitrage value is really limited to the extent that the loads in your house are present to consume the battery capacity during that more expensive on-peak time of day period. And so if you're really focused on optimizing that time of day arbitrage, you might want to size your battery system so that you know you can use that capacity regularly during the on-peak period and discharge it from being full down to its low state of charge, if that's your goal. But if you want more battery capacity, you might need a second battery or a larger battery to have some left in the tank, for example, for a grid outage. So this customer who's got the whole house battery system designed for that time of day arbitrage is also going to have to be careful to turn off loads if the grid experiences an outage. That customer wants to be careful not to burn up all the capacity or energy stored in their battery on frivolous loads. They want to be careful to manage that consumption so that they continue to have power for their most important loads for the duration of that outage. So those are just a few examples of, again, how a battery that is designed to serve, one set of purposes really well might not work so well for another set of purposes. Ian and Matt, we just wanted to invite you guys to come back on and talk some more about other thoughts that may have come up during the course of our conversation, touching on some of these bullets, and then we can open the floor for Q&A in just a few minutes. Talk for a little bit if you're interested to share any more thoughts from that last slide I presented, or some of this content related to AC versus DC coupled systems.
Ian, you wanna go first?
Sure, yeah. So back to the consumption profiles, there's various monitors. I know Fort Collins has some for rent at the library. There's other units like the Sense and Generac PowerView that are available, and many other solutions available. So if you are seeking to understand your consumption profile and how much you use every month down to a granular level, I encourage you to reach out to your electrician or installer and deploy one of those and start understanding your consumption behavior and seeing how you can adjust it even without adding any type of investment to your home. You can certainly start your laundry later or earlier during the day, use your devices on various types of day, add timers, that type of stuff. So that's kind of the easiest way to battle time use rates without going full in on the battery investments. I also want to shed some light on, I think this crowd gets pretty excited about the future opportunities of batteries, as we all do. And yeah, there's a lot going on in Germany in regards to, and even in Vermont, the virtual power plants. And I think it's now becoming a more proven concept, is having these multiple homes connected to each other throughout a community, being able to deliver power at various times of day. That way we don't just shift the duck curve to the peak periods either. I think that's a key strategy that we'll see over time, is your battery system will be able to communicate with cars, vehicles, and other people's homes in order to flatten the whole curve and minimize the amount of carbon output that our system has. Turn it over to you, Matt.
Sure. Yeah. No, I think that's all spot on, Ian. I guess when I think AC versus an AC coupled battery versus DC coupled, I think if we think practical kind of applications, the number one I think is what's there already. So as an example, if the customer already has a standalone system, standalone grid tied system that's working great, there's a pretty solid argument from an overall cost perspective that something like a Powerwall or a standalone AC battery might be the most cost-effective way to add storage to that system. I think this is my personal take. I think if you look at a net new system where you're going to build solar and storage out of the gate on a brand new install, it's pretty hard to beat a DC coupled system in terms of kilowatt hours delivered or stored. And the reason's pretty simple: is an AC, there isn't such a thing as an AC battery. It literally is DC batteries and an inverter contained inside the same case. So when you think about it that way, you're duplicating components. And I'm not saying there aren't good applications for that or there aren't reasons to go that route, but if we think about the 80-20 rule, that's a steep hill to climb when you look at duplicating components. And then the whole house thing, here's another practical example of that. You might only want to protect 5 or 6 circuits in a house. But if those 5 or 6 circuits exist in a sub panel that's in the basement and the interconnections outside, you might spend, in electrical labor, you might spend a couple $1,000s to just separate those circuits out and get them up to the point of interconnection to even back them up, versus a whole house approach. That's just it's a practical example that we see a lot. The other piece of that is, I think everybody, I think Leland and Ian both agree, needs are changing. So what might work today might not necessarily work tomorrow. And we try to think about things in 10-year time periods for a battery, 25-year time periods for a system. So those are all pieces of this that go into design as well.
Yeah, I can't agree more, Matt. I think it was about 2 years ago, some of the systems like Enphase and Solar Edge were condoning their slightly older products as battery ready, and then now they have an entirely new line of equipment that's available at our hands and display that have impeccable controls. And so now there's almost like an option A, B, and C within each type of brand of inverter and battery nowadays to customize that to each customer's needs as well. So it's ever evolving for sure.
Mm-hmm. Well, thanks for those thoughts. And I would say, we certainly don't know what's going to happen over the next 5 or 10 or 20 years, thinking about the lifetime of that equipment, but we are entering an unprecedented period of change in the electric utility industry that's bringing substantially more intermittent renewable resources on to power the grid. And along with those changes, we're likely to see changes in rates and or rate structures over that 5, 10, 20-year period. So we don't know exactly what's going to happen, but we know change is going to happen. And I think battery storage provides customers with a lot of flexibility for responding to those changes in rates and rate structures. I'd like to open it up for questions to the audience. And Pete, I wonder if you have any questions that are already queued up that we should start with, or how do you want to manage?
Yeah, I've just been kind of going through some of the early ones. I apologize. A number of you did ask sort of ROI questions, so I'm going to kind of lump those a little bit together in general. And one of the points made was that with our relatively low cost of energy in Colorado, particularly, PVREA and up here in Northern Colorado, we enjoy even lower than average in the state, I believe. One of the comments was it is hard to justify, even with the time of day rate use cases. Any additional thoughts on cost justification, both now and potentially, do you foresee rate increases in the future that might be, what you're sort of hedging against?
Who's going first?
Okay. I'll let you guys take care of that one.
Go for it, Matt.
I think a couple things. Again, if you think about where solar was 10 years ago, I think it was really hard to buy solar on an ROI 10 years ago. People did it. I don't know how they did it, but they did. I think that's kind of where batteries are now. I will tell you that regardless of what the rate might be, the delta between off-peak and on-peak is only going to go one direction. And if you think about 10 years, Ian threw up a great slide that was like a 10-year ROI. I think inside the city, we're 1 or 2 rate changes away from that example being close to 5 to 6 years. That's my personal opinion. I think if you look at what California's done with rates and you look at how this is kind of going west to east, it's probably, again, not an if, but a when.
Mm-hmm.
Yeah, definitely.
I think those rates, oh, go ahead, Ian.
I think the utilities will continue to play off that, kind of curate their customer base and incentivize their customer base to deploy energy at the times that they need it most, because ultimately, like PVREA, they're going to be saving a lot more money if their customers are saving them their peak charges from tri-state generation, who charges them an exorbitant amount for going over peak and pulling more energy. So, the payback, and I think will overall improve in those utility areas. But we are seeing a lot of break even right now, and I'd say the customer profile from a financial play for these batteries is primarily people that are really excited about the technology, want to see their systems improve and grow, and really want to feel self-sufficient about their solar and battery choices. And I think over time that customer profile will change as much. Same thing we're seeing with solar, and there'll be many more reasons why people will choose to go with batteries. But I'd say ultimately the batteries that we do see often in PVREA territory, more of the rural cooperatives, are the people that value that intermittency and having that resiliency and backup, just to have that sense of security and or hedge their bets against that overall grid interruption.
Mm-hmm. I think that when you're asking questions about ROI, you need to also think personally about how you assign benefit to some of the other external benefits of the battery or solar system that you're considering. So it may not be a purely financial play, There's certainly some benefit to the resiliency of having energy stored in your home if there is a grid outage or some kind of a natural disaster. And you're the only one that can really assign a value to that. But ROI is also keyed primarily to the rates that you pay for buying energy from the grid. And increasingly, I think you'll see a distinction between the energy credit rates and the energy purchase rates. And so those energy purchase rates may fluctuate in ways that are different over time. We've referred to the on-peak period. You see those on-peak rates in your own bill, but the distribution utilities also have on-peak and off-peak kind of rate structures that they have to deal with when buying power off the grid from their wholesale providers or other generators that are selling on the wholesale market. So in that way, the rates that you see on your own bill are kind of related to these trends in the wholesale market or generation market. And those markets are going to go through a lot of change in the next decade or two.
Great. I'm going to move on to the next question here. It should be pretty easy. Can you do both kind of use cases for battery as a backup as well as to flatten the curve?
Can you repeat that one more time?
Can you pursue both of the use cases for a battery, both as a backup as well as to flatten the curve?
Yeah.
Absolutely.
Yeah.
I think Matt had a great slide there with the backup reserve power. So you're able to program the amount of reserve that your battery has, so you can have the level of backup, but also program your battery to maintain the load profile, or you can discharge it during time of day rates.
Right.
And both, I'll speak for the technology around SolarEdge and Generac. They're both coming out with end user controls where, as an example, if the snowstorm's coming, you can actually, right from your app, set the backup reserve to a higher amount for a duration of time. And it's a great question, but the idea around that is to, again, maximize the value of the battery environmentally and financially around that 99% period of time when the grid is up, supporting the grid, doing all that stuff. But if there's a concern for a grid outage, you can pivot and set that battery to a high reserve specifically for an outage. I think that's probably a perfect setup for, again, the vast majority of installs in the service area for everybody on the phone or on the webinar.
Mm-hmm. I love that feature. It makes it really simple for customers to kind of set it and forget it most of the time, but when they know the blizzard's rolling in, they can just whip out their phone and with a couple of taps, change the control system to like hold on to that reserve power, keep it charged all the way up in case the grid goes down, and optimize the way the battery's operating for that reserve power function.
Great. Next question. How does this residential battery system design apply to mobile storage like EVs equipped with vehicle-to-grid technology? And I'm going to kind of stack on another question. Kind of, does V2G really exist currently? Or how close are we to that? So kind of a double question there.
Okay.
Yeah,
we're not there yet, and for Collins, go ahead, Ian.
I was just going to say there's technologies to integrate the EV charger with your system components, so you can charge it directly from your battery and PV. But bidirectionally, I'm not aware of any technology that's available yet for that. I think from the technology perspective, we could be there to be bidirectional, but from a kind of a regulatory standpoint, I personally think it's going to take a while to be able to manage that bidirectional function and that ability because you're kind of crossing paths between the automobile industry, the renewable energy industry, the utility industry, probably a few more industries thrown in there to all work together to kind of create the system function. So I think there's been some pilot projects, but I haven't heard of anything commercially.
Right. In terms of shelf ready, like off the shelf technologies that are ready to deploy, I'm just familiar with a few examples of vehicles that are capable of that, and the inverters that are capable of charging the EV, from the same inverter that's managing your battery and your solar. But in terms of really getting to that ideal of being able to flow power back and forth from the vehicle to the home, and potentially, respond to signals from the utility, earn money from the utility for being able to do that, we're still quite a ways off.
Yeah, Leland, I'm actually trying to get Masood and or Pat at PRPA to do a presentation in the near future. Maybe I'll ask them to see where their smart charging study is, which would be that unidirectional to kind of use EVs as, in essence, dispatchable demand. But I just haven't heard the other directional flow get a whole lot of traction, at least here in the States.
Yeah.
Okay, and I think I'm just on to the next one, which is sort of on that topic. I hope that we covered that. Here's a good one. Do batteries degrade faster if you cycle them every day?
Well, that's a good question. Guess I'll go first on that one. There is a cycle count on the batteries. Generally speaking, if we think about a typical battery today, we're talking about some portion of lithium ion, lithium phosphate. Those batteries generally like to be worked a little bit every day. They need a little bit of cycle. I consider them kind of type A personality batteries. They got to be doing something. They don't do well just sitting there. But that technology is getting better. It's improving. I think, again, 80-20 rule, you can plan on using a battery daily, a new battery such as Tesla, Sonnen, Generac, LG. You can plan on pretty much using those however you want for a 10-year period and not necessarily getting hung up in a life cycle or a warranty issue during that 10-year span.
Yeah, that was great, Matt. I'll actually talk to the flip side of that. So keeping your batteries fully charged or fully discharged and not cycling them can also potentially degrade the battery. I don't remember the exact numbers in terms of the degraded efficiency, but yeah, if you maintain like 100% charge at all times, that will potentially limit the battery's ability to maintain its full life cycle throughout its lifespan.
Now, we could probably get into the details on this for a whole different hour's conversation, because there are distinctions in the battery chemistry that are interesting to explore when you're talking about this question of what causes battery degradation, and how much does that passage of time and also the number and amplitude of cycles and frequency of cycles, how does that kind of exercise of the battery contribute to the decay in battery capacity? But the main point to take home is what Matt said, that you know, with the batteries on the market, you can plan on using them for many, many years without having to worry about substantial decay. The lifetime of a battery is that word lifetime should really be put in quotes, because lifetime is defined in specific ways, like for solar panels and battery storage, as the point at which the battery reaches, is it 80% or 60% of its original working capacity? I think I want to say it's 80% for solar panels is considered their lifetime, you know, 20 years. And for battery storage, are those batteries, is it the same 80%?
It's probably maybe a little bit lower. It depends on specific applications, specific technology, but yes, that's pretty close.
Mhm.
Okay. Well, let's go ahead so we don't go down that rabbit hole any further. Next question. Say there is a long-term power outage situation. What happens to the extra energy produced from your solar array if you can't feed the grid and your batteries are actually at 100%?
Good question.
Yeah, go ahead, Leland.
Well, the solar array would have to cycle off. You essentially have to open the circuit so that you're not overcharging your battery. And that could be done a variety of different ways. It depends on the inverters involved.
Yep.
Okay. Next question. For the in-phase system shown by Ian, what is the typical PV system battery powers that you installed? For example, a 5 kilowatt PV and a 9 kilowatt hour battery. I mean, I guess, is there a standard sort of setup between the two?
Peter, were they referencing the difference between the two systems itself, or were they asking for like an average system size?
I guess, is there, I'm assuming, is there a recommended sort of size for the PV system itself that maps up to that battery size? Or do you have flexibility there?
I think there's definitely flexibility. I think Matt hit on it pretty good, that the 7.6 kilowatt inverter around that system size is really good, because you can plan around adding that clipping to the battery, maximizing your DC capacity. In regards to end phase, it's pretty expandable. You're actually more limited to, there's kind of a profile table in regards to how many microinverters you have and what your load capacity is in your house and how much you want backed up. And those kind of meet in the middle, and that determines your overall battery size that Enphase will let you install. And so that kind of goes through the design phase in terms of determining, you know, either what you want backed up and determining your overall size, or seeing what your PV size and estimating your, you know, what your goals are. Is it the backup, or is it the PV and overall return? That's kind of the balance, the trade-off.
Great. Next question from an Excel customer. How does being an Excel customer change the equation of best use of batteries?
Yeah, so that's a good question. So currently, Excel has, the last I heard as of last week, if you have solar, they're pausing your ability to go to time of use. I think that's only that's a temporary thing. I think it's going to go back to time of use mandatory for everybody. That looks like that's still in flux. I would say as of today, right now, if you're an Excel customer, the battery would be deployed in what we call kind of a maximized self-consumption mode, where it's trying to do everything it possibly can behind the meter to, either not purchase, again, flatten that curve, not push back onto the grid until kind of the battery was full or there's nowhere left to put the energy. But that's today. I don't think anybody is of the opinion that time of use isn't coming full on for every Excel customer, regardless if they have solar or not.
Mhm. It looks like that rollout will happen by the end of 2023 in Excel territory, right?
Yeah, there was a period of time where you could actually, so mid last year even, you could install solar and you could actually opt into the time of use, which depending on your design actually had an added financial benefit. Again, they've kind of paused that. At least that's what the folks at Excel are telling us recently. But to Leland's point, I think that's a short-term thing.
Okay, any other comments on Excel? Because we got a lot more questions. The next one is a bit complex. Can you please help everyone understand some of the nuances in interconnection applications, various jurisdictions and utilities with batteries for the various uses you defined for us? Although maybe we should limit that to Fort Collins, PVREA, and Excel for simplicity.
I think the easy answer is the interconnection applications for batteries are awfully similar to the PV applications in all those territories. So there's not a huge, like a significantly different department that handles all those. It's a pretty similar process that we go through with the PV.
I'll just throw in a little follow-up of my own. Are there any jurisdictions right now that are, shall we say, battery not friendly?
I would replace the word not friendly with
or not there yet.
I wouldn't even say that. I would say that there are a lot of areas that just they don't know. It's not that they don't like it. It's not that they don't want it. It's just this is a pretty new thing in the big picture, and I think it's gonna take a while. I'm gonna go off on a mild tangent. You don't even have to go to the battery side. You can still look at just the solar side. I mean, here's Loveland Light and Power, not 10 miles down the road, that is powered by Platte River Power Authority. So City of Fort Collins, those are two radically different approaches to putting PV on the grid. So I guess to back up off of that, it depends is the answer. And I think there's a lot of learning for everybody to do in the next, 8, 10, 12, 24 months.
Okay, next question. Any thoughts on smart electrical panels?
Are these the ones that are responsive to load shedding to help you optimize that duration of battery backup?
I'm not sure.
So I believe one product, I think it was called span.io, and it is a very nice product, I'd say. To replace your entire infrastructure with a smart loads panel like that would be a pretty penny. And actually, some of these manufacturers like SolarEdge and Enphase already have a kind of that smart loads control panel that I think was referred to. To educate a little more, the smart panel is almost like the breaker panel that most people have, but they have kind of CTs, monitoring devices on each breaker in the panel, and then they also rate the panel so it's easy to interconnect batteries and solar to it. Going back to the SolarEdge and Enphase, like Empower Switch, those automatic transfer switches kind of already are that smart control panel. And so adding those with that package already kind of happens. Now, if you're building a new home, asking your electrician or your engineer of the home to potentially add one of these smart control panels isn't too crazy. It'll add that consumption monitoring, that we've been talking about. That will give you the understanding of the electrical consumption of your home, and then it'll give you the breaker space and availability to add on these smart devices and/or power generation devices later on much more easily.
Okay, next question here. How can we invest in batteries when we don't know exactly what rates will be in the future? Are we banking on cutting the cord?
Yeah, good question. I don't think there's ever fully cutting the cord. There's usually regulatory issues around that and reselling homes. If you do live pretty rural, there may be opportunities. But to address the initial question, banking on the future rates, I think, right now we're seeing the worst rates of them all for batteries. And batteries give you that flexibility to deploy energy whenever you want to. So you can reprogram that batteries to maximize the value of your solar energy system and your battery investment. So if time of day rates, if peak rates moved all of a sudden to, around midnight, you'd be able to program your battery to maintain that charge and discharge during the night to accommodate for a shift in those types of rates.
The flexibility in the software is giving you a hedge.
Right.
Yeah. Yeah, I don't think anybody's banking on cutting the cord because it's kind of, it doesn't make sense financially to pay for a system that would provide you the full off-grid capacity that you might see in an off-grid cabin installation. Yeah, it doesn't make sense to, at this point, to invest in that much capacity if you're already tied to the grid.
Yeah, I like to quote, I think it's Dan Fink, who I haven't give an off-grid presentation in a long, long time, but he always starts off his presentation that the best battery ever made was the grid. And for a guy who builds off-grid, he kind of really, really dissuades people from cutting the cord.
Mm-hmm.
Okay, here's a good open question. What new battery technology is on the horizon, and what do you think about, vanadium batteries, I guess other chemistries? And I'm going to sort of add in another comment that somebody made about, kind of asking about declining costs with just standard, lithium chemistries.
Yeah, I think there's a lot of unique research that is now getting invested in. And like, for example, even locally, Predo Energy, I don't remember their exact cell type. Perhaps someone knows their chemistry here in this group, but I know they recently got a huge investment to start commercializing their battery. And I think it's incredible. It's huge competition, huge amount of money flowing into the space. Like I said, there's a lot of niche market opportunities for various types of batteries. You have all the way from flywheels for utility scale to lithium ion for residential time of use to nickel cobalt and lead acid for off-grid applications. And that's only scraping the surface of the various cell types. So I'm curious to see where like saltwater flow batteries are going, vanadium flow. I think it's a really exciting time.
Yeah, Prieto, by the way, is a 3D copper foam that's electroplated with lithium, and it's a solid state chemistry, if I'm recalling correctly. I've tried to get her to talk, but they're kind of busy ramping up, shall we say.
Yeah.
Okay, so here's a really good one. Can you talk about the carbon footprint of adding batteries? That is kind of a deep life cycle analysis question, but I don't know if there's any ready, available information.
Carbon cost of the battery that you're buying, essentially. Good question.
Yeah, that's an excellent question. I think if we had a PhD student or a university professor in here to kind of speak to that, I think it's been well known that the peak shaving and offset of the carbon from the batteries outweighs its life cycle, but I don't know the exact numbers to put anything to it. But.
Right, I don't either. I don't have that.
I would think it's very use dependent, and a lot of factors are going in. What's the load if you were in, Nebraska Power District or a district where you've got 80% from coal and the rest is from natural gas? It's actually going to have a lot better carbon payback than right now. We're at roughly 50%. But no, that is a deep question. And
definitely, and it's not as easy as like solar where you can punch in the kilowatt hours and relate that to the carbon equivalent offset. Like you said, Peter, you have to kind of equate to how, where, when that battery is used in order to fully calculate the full carbon impact.
Right. I think it's important to consider those cradle to grave or cradle to cradle cycles as we're thinking about the technology solutions to our energy future. All of these high-tech solar arrays and batteries are certainly depleting finite resources on the planet. And so in addition to that carbon cost, we have to think about where are all those raw materials coming from, and how much longer can we actually tap those resources. So it's important to think about how your solar array is going to be recycled and how your batteries could be recycled and repurposed, once they reach a certain point in life.
yeah, that's going to be a big topic at the Solar 2021 conference in Boulder in August. And I know Baywa Ray, if I'm even saying their name right, who's a major distributor, they're really involved in recycling the panels that they're distributing. And I know I'm sure they're looking at batteries and the total balance of system. Okay, next question here regarding rates. The electrical resource plan in front of the PUC for Excel thinks their rates will rise only slightly to 12 cents over time. Okay, that was just sort of a comment. Anyone have thoughts on that?
I mean, I think that what their rates rise versus what their on-peak and off-peak rates are two different things. I guess the short answer is we'll see. I think the best predictor of future behavior is past relevant behavior. And I think that ship already left the dock. I might be biased in this conversation, but I guess that's my 2 cents.
Okay, great. Anyone else for the next question? Okay, so we still have a lot to go, and only 19 minutes. Are there utility providers that mandate they have control over use of stored power for the grid load support?
You mean for customer-owned batteries, or for utility?
Yeah. Well, or is there an example where I feel like Green Mountain Power has something, but I don't remember the details.
Right, some of those larger utility-sponsored programs or projects, Green Mountain in particular, they're going to use those batteries when they need them to support their either reliability or economic needs. But the customer has the benefit of that storage located on site if the grid goes out.
Okay.
And you look at the Solar Lofts installation in Rocky Mountain Power Territory over near Salt Lake. The customers in that demonstration are renters in an apartment complex, and they have some benefit of those batteries being located on site, but the utilities really cycling those batteries for their purposes and managing wholesale costs.
Okay, so not quite yet, although I think as the future of DER strategies evolve, we couldn't rule out some sort of more of a mutual agreement where they might, just like we talked, the whole vehicle to grid thing, it would be probably more realistic for behind the meter batteries, having a partnership agreement with utilities.
That might look like the same kind of program that Excel or Collins has set up for incentivizing customers to participate in a peak power program where the utility can perhaps cycle their air conditioning compressor for a certain period of time during the hottest days of the summer when they're the most expensive wholesale energy prices. So yeah, there's programs out there already like that, and I could anticipate a project like that in the Collins Utilities territory too.
Okay. Next question. How much energy is consumed in the charging process, and what is the efficiency of the conversion, I'm assuming, of the charging process?
It's on the order of 98% each way, 97, 98% efficiency in and then coming back out. So round trip efficiencies on the order of 95%, 96%.
Okay. A follow-up to, I think this is the follow-up to the earlier question on utility control, is there any kind of mandatory sellback of energy, or can you, obviously, I'm assuming you might be able to sit on it as long as you want to and use it as you wish, correct?
I think there's two kind of portions of that to kind of look at. The utility really has no control over how you manage your energy behind the meter, and that's a very important piece. So we talk about maximizing self-consumption behind the meter energy management. The meter can only see what the meter can see. So if you're just matching a load in the house with your equipment, the meter is effectively blind to that because you're not pulling from the meter. So that's one half of it. The other half of the question, I think, is it's only a matter of time before I think every utility starts recognizing the value of not only distributed generation going on the grid, but distributed generation going on the grid when the sun is down and during peak time of use. I think it's only a matter of time before they start valuing that higher and higher. Fort Collins is a great example of that. You know, when you put power back onto the grid during peak time of use, you're putting it on at a much higher rate than non, off peak. You're putting it on really darn close to what that rate is you would be buying for during peak time of use. I think that just from a common sense perspective, the value of putting that power on the grid during that time it's only going to continue to go up, because that's really hard to make that power during that time period from a green, with a low carbon footprint.
Mm-hmm.
Okay. Quick comment that came in is the Hyundai Ioniq 5, I guess, is programmed to be able to be actual vehicle to grid. So there is one.
A quick comment on that, and I think Ian touched on this. From my perspective, the hardware's there, and most of the software's there. You can right now. I keep coming back to SolarEdge because there's a lot of them out there. You can right now integrate a SolarEdge EV charger with an inverter. You can look at it in one place on an app and really effectively choose whether or not it's going to take power off the roof into the car or from the grid based on programming. My 2 cents is I think the limiting factor around all of this is really the warranties and the battery manufacturers of the cars, because these cars were effectively built around the battery limitations of driving down the road, not driving down the road, then parking in the garage and having the battery cycle a bunch more because it's feeding the house. You mentioned Hyundai. The Nissan Leaf was marketed as bidirectional. I haven't dove into the details about what that actually means, but again, I think we're around a regulatory limitation, not necessarily a hardware perspective limitation.
Okay. Here's a good one. We're back to battery chemistry, but I think this will be a good one. Please compare lithium iron, I believe that's phosphate, and versus lithium cobalt phosphate, which is better for the environment. And I'll just ask, because I believe I'm asking the right question here, any other considerations between the two chemistries?
Yeah, I think the debate goes back and forth between the two. I think there's phosphate that was always considered potentially hazardous, but we found that there hasn't been significant thermal runaways in any of the most recent models. All of them have been deemed safe and under warranty. I think cobalt has a higher operating temperature range, but it's still pretty limiting. And so that's why most batteries you see are in garages or closets. They're both very similar technologies in my opinion, and I haven't seen a significant difference to really push one out of the way over the other one. I don't know what you've seen, Matt.
Out of my wheelhouse and skill set for sure.
All right.
Yeah, the only comment I would throw in is the cobalt situation, being in the situation and always highlighted in Congo, and I think in other parts. That would be the thing I would throw in. But again, I'm sure there's a life cycle analysis out there. But I've seen plenty of several recent articles, and yeah, it's definitely a lot of opinions on it.
Yeah, I would think that the lithium iron has a lower environmental footprint, but that's also not something that I've gotten deep into to fully understand that. That chemistry is also proven to be a little more stable thermally, and definitely low risk and long life cycle. Those batteries I've seen those batteries have a lot longer warranty period in terms of number of cycles.
Okay. Also, I'm going to answer the next question, just so everyone knows that this is being recorded, and GoToWebinar will automatically send out a recording to all attendees. Usually it'll be tomorrow or the day after. It's usually within about 2 days. Also, there are handouts that you can, if you want to have the slides, you can download from the handouts as well. So next question here. Please recommend 1 or 2 books that you feel best explains PV battery options for the residential user.
I don't have
or perhaps online resources.
Okay.
So it depends what specifically you want to get into. I guess if you want to know from like a personal DIY perspective, there's like Solar Energy Institute has some good flavor of like how the industry works and how to do all that and how to get involved. There's an education and let me look it up real quick. It's escaping my mind right now. It's bothering me. There's a California kind of institute for off-grid. I'll send out a link to Peter later with a link to that, but that will further describe kind of like do it yourself, learn about the basic concepts of grid versus off-grid and kind of everything we talked about today. So I'll send that link out to you, Peter, and you can disseminate that as well.
Yeah, Ian, are you talking, is it the group that evolved out of the original Real Good Solar?
Yep, that's it.
Oh gosh, yeah, I forget their name too. Yeah, that's the only thing that's still surviving out of that. Big RGS, I think, went under.
Yeah.
Okay, I think we're at our last question here. Somebody had to throw in one more.
Last question, just for 101 kinds of learning. Energy Sage is a good resource online. And I would also recommend Solar Energy International for their coursework. And that's more focused on teaching people skills to be able to do it themselves or take on a career in renewables.
Okay, if Platte River Power gets to near 100% renewable energy supply, can you talk about how that changes the motivation to put solar on local roofs?
We could talk about that a little bit. I think if Platte River is achieving 100% or near 100%, and that's Platte River's goal by 2030. I think PVREA and Excel have put that goal out at the 2050 mark. So I think that'll generally drive some people to focus more on economics, right? Certainly there's different factors at play here. One is the thinking on the value of having distributed generation placed locally where the load is. So owning your own generation and being self-sustaining is a high value for some people. But if Platte River is headed this direction to achieve 100%, that will essentially spread the cost of renewable generation or delivering 100% renewable energy to all of the customers within Platte River Power Authority's service territory, ultimately, I would think. And so that'll have some economic impacts in the rates department, and it will lead people to thinking more about the value of, do they want to own this generation and have it available for them on their own roof, and give them that kind of resiliency aspect or not. I'm interested to hear Ian and Matt's perspective on that as well.
Sure, I'll take a swing at it. I mean, I think that there's a math problem there. You know, when you look at the adoption of electric vehicles, I think that the distributed generation side is going to start becoming more and more valuable. So the conversation is going to shift. You know, again, backing up and looking at the trajectory, the question used to be, do you want to produce clean renewable energy from your roof, or do you want the mean power company to give you coal-powered electricity? It's going to quickly change to, do you want to have distributed generation to support the grid, or is the utility going to provide green electricity at a higher rate? I think that's really where it's heading. I think it is actually the electric vehicle adoption, pun intended, that is driving a lot of that. It's going to drive it faster and faster. So that's kind of my take. And full disclosure, if any utility makes it to 100% renewable generation, I consider that an absolute win for every single person listening to this conversation.
Yeah, distributed energy overall is hugely important for our grids, you know, trying to transform them from these central power producing plants where there's not enough wind source available typically at those same power stations, nor is there typically the land space for enough solar to support the same amount of power generation that these coal power plants did. So instead of you know, distributing that amongst all our rural areas, there's plenty of resources with locally that are needed in order to meet the 100% demands that we're asking for, especially with a growing grid in terms of population, electrification, and all that. So it's not only up to you know, commercial businesses, residents. We're going to see a strong mix of kind of everything: wind, solar, potentially hydrogen, all, and batteries, all, and electric vehicles, all playing together, managing a part of the smart grid and our communities, and making them more, not only more sustainable, but more resilient as well.
And I think to do that sustainably, people need to take a good look, critical look at their own energy consumption and consider how we can all live more efficiently and not buy into the idea that our energy load is going to keep growing and growing and growing exponentially. California is a great example of a jurisdiction that's been able to hold the average load per customer relatively flat over a period of decades, whereas other utility service territories that don't have the same kind of efficiency standard requirements have seen just load growth continue to climb and climb. So that's something that we have to pay attention to if we're trying to do this in a really sustainable manner.
Great. Well, we are up on 9 o'clock here, so I think I'm going to go ahead and wrap everything up. Want to thank Leland, Elon, and Matt for joining us. It was a great discussion. Thank all of you attendees and all of the great questions. If I miss any, I apologize. There was a lot to get through, obviously. Also, really quickly, Ian, I think you're referring to the Solar Living Institute out in California. So I think
yeah,
that's
and the
it.
book is called the Solar Living Source Book.
Yep. So, hey, everyone, have a great night, and look forward to seeing you at the next one. So, everyone have a great night.